Okay, it's past 3 p.m. So I think we should get started. Hello everyone to our first installment of our Distinguished Lecture Series seminars this term. As you know, the DLS seminars are the main high-profile event of our institute, the Max Planck Institute for the Science of Light, which is a means to engage the most important and influential colleagues in any area of the science of light. Here in the background or foreground, whatever, you see the program for this year. So we have managed to again line up a really excellent set of speakers. I want to point out that actually 5 of the 7 speakers are female, which was not by planning, it just happened that way, but I still think it's a really nice break in a field that is still heavily dominated by male actors, that we attracted so many talented, excellent, brilliant female colleagues to speak here. Corona still is very much in control of our lives. We had hoped that by now we could return to our normal mode of operation with the DLS seminars and have that in person, but that is not to be, and so we have to stay online, which of course on the one hand means that it's rather unfortunate that we cannot allow as many contacts between the speakers and many people at the institute, have lab tours, have a nice dinner in the evening, etc. But on the other hand, that means since it's online, it also gives an opportunity for a lot more people to join these presentations. So I particularly want to welcome anyone who is joining us from outside of our institute. I think it's a good moment to also say a few thanks. For one, Sylvia Kuzminski, one of our group leaders here, has helped me greatly to put together this program, to contact speakers, etc. I want to thank Lothar Kuhn and his team, and also Lisa Spann, who have worked in the background to set this up. Before we get to the science part, I still have 2 technical announcements. So for one, we are recording this presentation. So I want to make you aware of the fact that we are doing this, and by you continuing to participate, you implicitly agree that you might be recorded in case you have a question, you speak up, etc. And the second technical announcement is that I would like to ask every one of you to mute yourself during the presentation. If you have a question, then please type the letter Q into the chat so that we know that you have a question. Most questions will be answered at the end, and I would then ask you to unmute, ask the question. You can have a short conversation back and forth with our speaker, and then mute yourself again. If there's anything urgent during the presentation, you can also type a Q, and then we can see whether we can slot that in. So now, after all these introductory words and technical remarks, let's move on to the science part, to the fun part. It's a great pleasure to introduce and welcome the first speaker of our DLS series, John Dudley. John is a distinguished professor of physics at the Université Blanche Comté, if I say that correctly, and also at the CNRS Femto in Besançon in France. He has worked on many areas that are of interest to our institute, including ultrafast measurements, and also more on the interdisciplinary side, extreme events. Also in the talk today, we'll be talking about that in nonlinear fiber optics. He's a fellow of many societies. He was the president of the European Physical Society, and also initiated the Day of Light in 2015, if I get that correctly. So I think a very, very good example of the kind of caliber of speakers that we try to attract here. So we are very, very happy that you agreed to speak. And without a lot further ado, I want to hand over to you. And we are very much looking forward to your presentation.
Okay, so thank you very much indeed for the introduction. And I'll just say before I share my screen that it's a real pleasure for me and an honor to be in Erlangen and speaking to you all, both colleagues and friends for many years, and it's a pity we can't be together in person, but that's the way things are, and let's just see if we can enjoy an hour or so together talking this afternoon. So without further ado, I'll share my screen and hopefully everything will run smoothly. The topic of this talk is on ultrafast measurements and the link with nonlinear fiber optics and how we've used advances in measurements to identify new classes of so-called extreme events. The work was not carried out just by me, of course. There was a whole group of people over many years. This work now goes back to 2007 and even earlier than that, and some of the genesis of the ideas. So I have to acknowledge everyone on that list and many more. Before I talk about the particular science of extreme events, I think there are a couple of very nice historical conjunctures that happened this year, and I'm going to introduce them from time to time as we go through different parts of the talk. The first and the most obvious is that last year was 60 years since the laser was invented, and this year is 60 years since the first experiment on laser-induced harmonic generation. Now, this is the famous paper from Franken out of Michigan, which reports the second harmonic generation of light from what we now call a Q-switch Ruby maser. The problem is that this particular paper doesn't show the evidence for the second harmonic generation, because where it should have appeared in the photographic plate, it was removed by the typesetters of the journal PRL. What's really interesting, if you've never done this, have a look at the American Institute of Physics Niels Bohr Library and Archives, because they have oral histories of with hundreds, many hundreds of physicists from the history of our field and many others. And you learn all sorts of things, such as the second author on this paper was doing the work as an undergraduate project. And they still felt that his contribution was enough to put him on as an author on this very important paper, which I think is fantastic. Interestingly, nonlinear optics itself was considered much earlier than that. The first reference to any kind of nonlinearity involving light was in 1926 by Vavilov in Moscow. And there's a 1996 paper from Physics Today, which gives some of the references and the history to that. In 1930, the PhD of Maria Gopet-Mayer studied two-photon absorption and many other nonlinear processes. And the word nonlinear optics itself was introduced in 1950 in a book called The Microstructure of Light, also by Vavilov. What's interesting is that although we often associate nonlinear optics with Bloembergen was in fact a very good friend of many of the leaders of Russian nonlinear science and nonlinear optics. And so a lot of the Soviet Union ideas of nonlinear optics are transferred naturally into the work carried out in the USA. I might say more about that later if there's time. That's some of the history of nonlinear optics. Now, the topic of the talk is on extreme events. So first of all, I have to define what they are. Well, one way of defining them, the useful working definition, is that they are events that are rare, unpredictable, and often highly destructive. So in the natural world, we'd associate these with disasters such as earthquakes, floods, fires, and so on. They've been the subject of mythology throughout the history of humankind. All cultures from all places on the planet have their own stories about the origin of catastrophes and so forth. And in the 20th century, we are the field of extreme events for about 30 or 40 years has started to evolve into a very important and separate area of research that is very interdisciplinary and which combines areas of some specific expertise such as geology or climate or oceanography together with a cross-cutting expertise in areas such as nonlinear physics, multi-physics, simulation, statistics, artificial intelligence, and so on. So it's a really interesting field of research, and it was fascinating for us in optics to be able to get involved in that. Now, the particular link between optics and extreme events came via the rogue wave or the extreme wave or the freak wave of oceanography. Now, these rogue waves are large and destructive waves that appear on the ocean. And what makes them exceptional is that they appear outside the range of amplitudes that you would expect based on models using linear wave theory. There are tales of large waves in the literature going back centuries. The first estimate of a wave height was in 1933 from a US Navy ship, which was able to perform a geometrical estimate of a wave height of about 30 meters. And since then, there are photographs now that are very common of these giant wave events around the world. Now, what made the science of rogue waves more quantitative was a measurement in 1995 on New Year's Day from an oil platform in the North Sea called the Dudley platform. And using a downward pointing LiDAR system to measure wave height based on reflection, they were able to record a pattern of surface displacement over many hours, and with the I have to be a bit careful about my words here, with the average, if you like, a moving average of wave excursion of plus or minus 5 meters. Now these are big waves, okay? They're long wavelength, hundreds of meters, but they're still very big. But then at one particular point, a giant wave appeared in the record with a wave height of around about 20 meters from trough to peak. And the fact that it appears as an isolated event in an otherwise relatively uniform time series, uniform relative to this event, made people in the field of oceanography sit up and really pay attention, because this meant that you could record these rare events. They did exist. They weren't just photographic or anecdotal. They were real events. You could measure their waveforms, and this opened up the field. Ways of measuring waves over many months or many years have been carried out using wave buoys, but this result highlighted that many of these measurements would not capture transient events like this. If they measure something like an average wave height over half an hour or so, that's not going to be enough to capture a transient. So a typical wave height distribution obeys a Rayleigh probability density law with long tails. Rogue waves would appear right out here in the extreme long tails. And they, in fact, they would appear at a probability which was greater than that expected based on a Rayleigh calculation. Where this entered the field of optics was in 2007, where measurements of the statistics of supercontinuum generation, which is a phenomenon known to many people in your institute, revealed that at certain wavelengths, if you analyze the time series of power or intensity at particular wavelengths in the supercontinuum, and specifically at long wavelengths, then this time series would occasionally show extreme peaks. And if you plotted a histogram of these power or intensity peaks, you obtained a very long-tailed distribution, much more long-tailed than a Rayleigh distribution. So the analogy was made that these intensity fluctuations in the supercontinuum could be considered analogous to optical rogue waves. Now, the context here is something very interesting, and you can tell I had a lot of fun putting the slide together, because in writing it, I realized that this year is not only the 60th anniversary of nonlinear optics, it's the 30th anniversary of the concept of the photonic crystal fiber, because these slides, which somehow I managed to find on the internet from one of Philip Russell's talks, shows that these are notes made on the 13th of May, 1991. And without the photonic crystal fiber concept, we wouldn't have had the dispersion control or the dispersion engineering to be able to see supercontinuum generation. Now, we all know that the International Day of Light is celebrated on the 16th of May. And for me, the 13th of May is within experimental error, the same as the 16th of May. So maybe this year we can change the logo a little bit and put some holes in the middle of the International Day of Light, sun, and make a particular celebration in the Max Planck Institute for the Science of Light, just focusing on the photonic crystal fiber concept. Now, it's not only the 30th birthday of the photonic crystal fiber, it's also the 30th anniversary of the Curlin's mode-locked titanium sapphire laser, which was reported in January 1991. And what's interesting about this is that it was an unexpected experimental discovery, and it very rapidly led to the realization that these femtosecond lasers operated with many of the same physical mechanisms as short pulse propagation in an optical fiber. And so it allowed a lot of the theory that had been developed to study optical fiber solitons to be transferred more or less directly into the field of studying lasers. What we call today the dissipative soliton laser had its origin as a concept back in 1991. And this led to the famous master equation of Hermann Hauss for studying self-mode locking or passively mode locked lasers in a perturbative regime, and more extensive transfer models that Ferenc Krauss and Thomas Brabeck put together. And these ideas will become a bit more important when we start to talk about lasers and real-time measurements. One of the things I like to point out when talking about the mode-locked sapphire laser is that it's a really nice spatio-temporal example of a soliton balance, because for those of you who understand the details of this, you know that there's a spatial Kerr lens that acts as a saturable absorber when combined with an aperture for intensity discrimination. And in a sense, this is a diffraction management mechanism based on a kind of a spatial soliton. And this spatial soliton idea is combined with a temporal dispersion management idea through cell phase modulation and dispersion control through prism pairs to create the stable femtosecond laser operation. So that's a nice little slide for the experts. Now, I talk about that because it allows me to also go back a little bit in history, to go back to a year where self-focusing was first discovered. And self-focusing itself was a nonlinear effect. And it was discovered in 1964 experimentally when light from a Q-switched ruby laser was focused into glass, but instead of spreading out, as you might expect through diffraction, it created its own channel, which damaged the piece of glass in which it was being focused. And Michael Herscher, who saw this, realized it was unusual, and Charles Townes realized that this might mean that optical nonlinearity through self-focusing was offsetting the natural tendency of a beam to diffract and to create some kind of self-trapped optical wave. And the famous paper now from October 1964 with Elsa Garmeyer and Ray Chow wrote down what we now call the nonlinear Schrödinger equation for the spatial propagation of a light wave in a nonlinear medium. And it was also the first statement of a hyperbolic secant solution of this nonlinear Schrödinger equation. Now, this is interesting. It wasn't actually the first statement of the nonlinear Schrödinger equation because that had been done in the Soviet Union in 1962. And the school of Moscow nonlinear physics, led by Akhmanov and Koplov, was extremely strong. And they worked hand in hand with a lot of the colleagues in the United States to develop the field in the 1960s. Bloomberg eventually got a Nobel Prize for nonlinear optics. Koplov and Akhmanov did not, but on the other hand, they got a nice painting of themselves when they won the Lenin Prize, a nice painting of the two of them riding a horse. And down the bottom, you see a nonlinear crystal where the red light is being converted into green. So I'm not sure what's more important, a Nobel Prize or a nice Soviet era mural, but I think they're both pretty nice. No one seems to know where it is now, but that's a different story. Now we can get back to the more contemporary science. So we've set a scene where we've introduced ideas of nonlinear trapping and nonlinear Schrödinger equation, extreme events, rogue waves, and time series. And so what I want to do now for the bulk of the talk is to talk about supercontinuum generation, talk about where it led us, and look at some ideas of where we can go in the next 5 to 10 years. So the nonlinear Schrödinger equation that Townes wrote down describes spatial self-trapping because of a nonlinear refractive index, which would cause light to self-focus, and diffraction that would cause light to spread. So any physical system that contains these two mechanisms in the right way will have an analogous nonlinear Schrödinger model. So a light pulse in time propagating in an optical fiber will obey a nonlinear Schrödinger equation where a pulse will temporally compress if it's nonlinear, because of the nonlinear refractive index, and temporally disperse because of dispersion. On the surface of deep water, an envelope of waves. So the difference, we're always talking about wave envelopes in the nonlinear Schrödinger description. So I hope this is clear from these figures, which show the carrier oscillations underneath the envelope. So the envelope of a wave packet on the surface of the ocean will also obey a nonlinear wave equation. Waves disperse, which is the linear term, but for large amplitude, the wave speed becomes dependent on intensity in the same way that the wave speed becomes dependent on intensity in optics. So you end up with the same mathematics. What's very interesting is that since the 2007 realization that there's an analogy between light wave propagation and oceanography, these analogies have popped up all over the place. So Ulf Leonhardt came up with the idea of an optical event horizon. This led other optical models for different gravitational effects, relating in definitions of what you might call event horizons, and some claims, although they're disputed, of a Hawking radiation analogy, and even a recent paper proposing optical models to test supersymmetry. So this is all very interesting, and it all goes back to this simple idea that if the same physics can be modeled in an optical system coming from somewhere else, then you can try to make some contribution to a broader field of study. So what we set out to test in 2007 and was, first of all, in the particular case of optics and ocean waves, is this analogy really valid? Okay, so first of all, is it just a load of hype, or is there something real there? And the key point was trying to determine whether we could use optics to answer what was a burning question in oceanography, which was whether ocean rogue waves are governed by linear or nonlinear effects, or both. And this is a useful definition, very simple, obvious definition of the difference between a linear and a nonlinear wave. A linear wave, its properties don't depend on amplitude. A nonlinear wave, they do. Okay, mathematicians like to cast these definitions in terms of solutions to particular equations, but I think talking about the physics is a lot clearer. So first, before we get to oceanography, I'm just going to review how a supercontinuum forms and where rogue waves are generated within the supercontinuum. So we start with the optical form of the nonlinear Schrödinger equation, which involves group velocity dispersion and a Kerr-type nonlinearity. Dispersion on its own changes the temporal pulse shape, but does not alter the spectrum. Nonlinear self-phase modulation on its own will broaden the spectrum, but it doesn't alter the temporal intensity. If you calculate the local effects over an infinitesimal distance of dispersion and nonlinearity, you can find that these two effects can cancel, and this cancellation leads to optical solitons. The fundamental optical soliton, which is a hyperbolic secant pulse, is observed for a particular combination of power, dispersion, and pulse duration and fiber nonlinearity. And this leads to an invariant pulse that propagates in principle forever in the time and frequency domains. The soliton dynamics can also lead to recurrence or periodicity, where an input pulse will breathe periodically with evolution. And there's mathematics from inverse scattering that allows you to describe all this rigorously and beautifully. The problem is that once you go beyond the simple nonlinear Schrödinger equation to model a real fiber, then things become more complicated than the nonlinear Schrödinger equation, and we have to generalize it. So from a simple model with just two terms of dispersion and nonlinearity, we have to introduce higher order dispersion, optical shock formation, delayed nonlinearity through the Raman effect, and so on. So this is a talk in itself, so I'm just going to skim over this. But the key concept is that although self-phase modulation and dispersion on their own would yield perfectly periodic evolution, once you introduce these higher order terms, you see a process called soliton fission, where the periodic evolution that you would see in an ideal case in the spectrum or in the time domain will be perturbed and the pulse will break up. And there are two key elements of physics in a silica fiber that broaden the spectrum. The Raman effect will shift things to longer wavelengths, and dispersive waves or Cherenkov radiation analog waves will shift things to shorter wavelengths. Now, in the more recent work being done in hollow core fibers with gases, there are many more, there's a lot more physics which comes into play involving ionization and so forth. But here I'm just going to restrict the discussion to the historical idea of silica fiber. Interestingly, this was all worked out in 1985, which we discovered later, but that's okay. It was done by Dyanov and Prokhorov and others, again in the USSR, where they saw the same thing. They saw it in black and white, we see it in color, but it's exactly the same physics. So if you solve the nonlinear Schrödinger equation for the realistic case of a supercontinuum, where you're actually solving the generalized form of the equation with higher order effects, then you can model the evolution of an input pulse in time. You can model it splitting up into different temporal components, and you can model the spectral broadening. So these parameters here are absolutely typical of the early experiments done in 1999 and so on. And if you plot this not by taking slices through the evolution, but by looking at the whole thing in a false color plot, you start to see some beautiful physics reveal itself in terms of the appearance of discrete dispersive wave components, long wavelength Raman components, solitons in the time domain, dispersive waves that spread out, and so forth. The key thing, of course, is over here, which is when you compare the prediction of the model on the bottom with what you see in experiment. And the agreement is not perfect, but it's sufficiently good to give you confidence that the model was working and you understand what is going on. So this is a nice way of understanding it. The problem is that experiments did not always show nice structured supercontinua like this. So the simulations will predict a supercontinuum like this with all these spectral peaks that are well defined, and in particular this long wavelength peak over here. But what you would often see in experiment was something like this, which was nice and flat. And although you might think that this flat spectrum is actually preferable to this structured spectrum, from the perspective of frequency metrology, which was one of the key applications of the supercontinuum, which led to the 2005 Nobel Prize, or half of it, these smooth spectra were found unsuitable. So the question was, what was going on? And it was here that these generalized models that you could rely on, because they agreed with experiment under certain conditions, they revealed that if you had a long input pulse, or if you had a short input pulse but lots of noise, then the nonlinear evolution in this model became chaotic. So very, very small differences in initial condition would give you very large differences in the output temporal and spectral characteristics. So these 5 results here show 5 different spectra that correspond to identical initial conditions apart from a quantum noise or an approximate quantum noise model. And it's very clear that they're very different. And it's also clear that the smooth spectrum you see is an artifact. And so the physics here is that these nonlinear processes, such as soliton fission, are very sensitive to noise, and spectral components outside the initial bandwidth can grow. And since that growth is not from the coherent input of your pump, there's no phase relationship, and that destabilizes the subsequent evolution. The fundamental origin of where this instability comes from is a process which is as fundamental to physics as almost anything that you can think of, and it's called the modulation instability. It's a fundamental property of nonlinear systems where modulation, noise on a continuous wave solution will experience exponential growth. It was first studied in the 1960s in the case of water waves, and it was shown that it would lead to new spectral components and the growth and the decay of localized structures in the time domain. If you study this process in detail, you realize that you can basically split its physics into two regimes. One is when your initial modulation is coherent. That is, you have well-defined sidebands with well-defined amplitude and phase. And in that case, modulation instability leads to what we call solitons on finite background and breathers. When it's stimulated by noise, these breathers and solitons become chaotic, and we see rogue wave statistics and extreme events. So that's the basic physics. In fact, there are even the same physics of modulation instability also occurs in astrophysics, in dusty plasmas. And there are even proposals that all of the initial localization of the universe, which led to the formation of stars and solar systems, arose somehow from a fundamental modulation instability. So that would be a wonderful result if it's studied. Modulation instability has been studied by many people from all sorts of different fields. The only comment I'd make is that it was almost discovered in 1947 by Bogolubov, who derived a nonlinear Schrödinger equation in the context of superfluidity, what we'd probably now call a Gross-Pitaevsky equation. But he noticed that the solution had a stable and an unstable branch, but he thought the unstable branch was not interesting. So he almost discovered soliton physics from the nonlinear Schrödinger equation before anyone else, but it took 20 years after that before it was rediscovered. So now, before we talk about the noisy consequences of this instability, one of the first things we did when we realized the importance of modulation instability to the supercontinuum was we actually studied it outside the supercontinuum in a more controlled case where we create frequency domain initial conditions based, for example, on two stabilized lasers beating together. We injected these in different lengths of fiber, and we saw whether we were able to create the mathematical solutions for modulation instability that are expected from the nonlinear Schrödinger equation. And in fact, we can. So based on this coherent modulation, we are able to create in the laboratory whole families of nonlinear localized structures out of light. And we can study their properties in time and in space. And all of these results since 2010 have been experimental and theoretical, and it confirms that you can create a nice, clean, nonlinear Schrödinger equation system in optics to see these things. And these results had a practical impact in essentially reminding the oceanography community that they were the first to look at this in the 1960s. And so that field of research in oceanography had essentially been forgotten since the early work, and it was then reactivated by the work in optics, where researchers would go and they would create rogue waves, deterministic rogue waves in water wave tanks, and even perform experiments testing the resistance of particular boat shapes to these rogue waves when they were generated and when they were directed towards the ship. The problem you have, though, is that whilst it's easy to measure a modulation instability solution that is stable, it's much more difficult to measure one that's unstable. And what was special about the 2007 measurements was the use of a real-time measurement technique which allowed these spectral fluctuations in the supercontinuum to be recorded in real time. And the technique that was used is now generally called the dispersive Fourier transform. And the technique works in the same way that far field diffraction works, and that with sufficient propagation in the far field, the diffraction pattern takes on the same form as the Fourier transform of the diffracting mask. The same mathematics applies if you study dispersion. If you have a pulse in time that has a temporal shape such as this one and a spectral shape such as that on the bottom, then with sufficient dispersion, the temporal profile will stretch to take on the same form as the spectrum. And we usually associate this idea with Jalali from UCLA. And it's certainly true that Bahram Jalali used that technique and applied it using modern technology. But again, if you go back far enough, the idea was originally proposed in 1983, well before the technology existed to make this useful. And again, in the Russian literature, they gave the unusual name of spectron to the particular pulse that has the same temporal shape as its Fourier transform. And that's kind of a nice thing. I've shown this movie many times before, but I'm going to show it again. It only takes 20 seconds because it shows how this works for those who have never seen it. And these are experimental results of a modulation instability field generated in a highly nonlinear fiber where the spectrum is fluctuating from shot to shot. To measure the spectrum, we put the pulses from the laser through its stretching fiber. It disperses such that the temporal shape of each stretched pulse now looks like the spectrum. And if you trigger your oscilloscope correctly, you can see the changes in the temporal pulse shape as each pulse from the laser pulse train generates a different modulation instability induced spectrum. If you take the average of this temporal signal, you get the red curve, which is shown in the figure, and it looks like part of it's missing, but that red curve is actually identical to what you would measure on a spectrum analyzer using an averaging spectrum analyzer based on a diffraction grating. You measure this curve up here. The average time domain profile is shown down the bottom, and they have different symmetry because one is plotting wavelength and the other is plotting frequency, but they have the same form. And this technique allows you to measure shot-to-shot fluctuations in supercontinua, and you can measure statistics, and it's now a vital toolbox to the way we do all these experiments. So being able to perform these measurements has allowed us to understand the fluctuations in more detail. It's allowed us to do more modeling. It's allowed us to look at simple questions like what makes rogue waves different in the supercontinuum? What makes one spectrum broaden like this and another broaden like that? What's the difference? And one of the things that has become very apparent is that collisions between these noise-induced localized peaks from modulation instability play an essential role in transferring energy between solitons in the continuum to allow one to become much larger than the other. Although solitons are often claimed to interact without any energy exchange, that's only in a pure energy conserving nonlinear Schrodinger equation system. In a real system with Raman and so on, it won't work and you'll have energy exchange. And so this allows the extreme events to develop. These real-time techniques and the focus on the real-time techniques also allowed us to look at the very early stages of the supercontinuum in more detail. That is, what's actually happening here. So before we have the solitons and all these really higher order effects, what about just the very fundamental process of noise-induced incoherent modulation instability itself? Can we measure that, right? And if we can, what does it tell us? Well, we can, but to do that, we can't measure that so much in frequency. It turns out that it's actually easier to measure in time. So the first measurements were performed using a time lens, which is another recently developed technology based on old ideas, where you create a temporal analog of a thin lens. So in space, a thin lens consists of three components: paraxial diffraction, quadratic spatial phase modulation, and paraxial diffraction. And so you can replace these three components by three temporal components. You just, dispersion is the equivalent of paraxial diffraction before and after your lens element. And the lens element itself is a bit more complicated, but it's a device that allows you to place a quadratic temporal phase on a dispersed signal through four-wave mixing with a linearly chirp pump. It's a bit complicated, but it works, and the physics is analogous to a regular thin lens. And so the setup here is a bit more complicated than the dispersive Fourier transform, but it allows you to generate modulation instability from a continuous wave laser, to stretch the femtosecond or 10 picosecond peaks to 1 or 2 nanoseconds, so that you can measure them using a 30 to 70 gigahertz detection system. And once you do that, you can reconstruct temporal pulse sequences that give you direct access to these temporally localized peaks from the modulation instability. You can perform statistical analysis on the peak heights. You can show that some of these yield rogue waves, as you expect from numerical modeling. And you can also compare the shape of the peaks with the coherent structures predicted from the noise-free modulation instability theory. So that's all very nice as well. I have about 5 minutes left, if that's okay. So, okay, right. So now we get to some ideas that are really quite new. So one of them is, what if you don't have a time lens? Well, it turns out that if all you can measure is the spectrum, I said before that measuring modulation instability through real-time spectral measurements was hard, and it is. But if you have enough dynamic range, it turns out that you can train a neural network to identify characteristics of the noisy localized field, such as the peak intensity, based only on the spectral measurements. To do this, you need a very high dynamic range spectrometer that can also operate at real time. So this is a 60 dB dynamic range system. It's constructed essentially by reducing the repetition rate of a titanium sapphire laser to 100 kilohertz so that you can scan mechanically a dispersed line spectrum across different points of a camera and reconstruct spectral amplitudes that way. So if you plot the evolution of these real-time spectra with shots from the laser, you see fluctuations and some very large spectra popping out at this point and at this point. And so the idea is that can you somehow, based on these high dynamic range measurements, can you use a neural network to create a transfer function that allows you to predict or correlate, if you prefer that word, the peak heights with the shape of the spectra. So the short answer to this question is yes, you can. You train, first of all, you use modeling to train the network with 30,000 simulations, and then you test it with another 10,000. And essentially, based on just recognizing the patterns in the spectrum, you're able to predict the maximum intensity of your modulation instability field. The bottom axis here shows the ground truth, what you expect from simulation, and the vertical axis shows the prediction. And the correlation is very good. And I don't think anyone would have expected that. The next question is, would you expect this? Can you do the same thing in supercontinuum generation with a neural network? And again, the answer is yes, but so far we've only been able to do this using simulations. So it turns out that just based on the shape of the spectrum in a supercontinuum, you can predict properties such as the amplitude, the width, and the delay from your time zero of the rogue solitons coming out of the spectrum. So you can, based on this complicated spectrum, you can predict properties of the temporal supercontinuum field. And again, what we're waiting for is for the experiments here, and they seem not so far away. And just finally, in the last couple of minutes, I can just review some work on lasers. May 16th is the date when we celebrate the invention of the laser. So concluding with a couple of minutes on lasers is a good idea. Although making stable lasers drives a lot of the industrial use of lasers, laser instabilities drives a lot of physics. And even in the 1980s, this was done by Herman Harkin, and there have been many, many papers since. The passively mode-locked laser, which includes nonlinearity and dispersion, as well as pumping and output coupling and filtering and other dissipative effects, gives rise to the dissipative soliton idea. And it's that which has driven work in studying laser instabilities for the last 10 years. And our work in this area has been to try to test a hypothesis about a particular kind of dissipative soliton laser, which combined together two different nonlinear elements. One was a soliton in one branch, and the other was something called a similariton, which is an asymptotic attractor that occurs inside an optical amplifier, to which any input will eventually evolve. And the hypothesis was that these lasers were more robust against nonlinear instability than other kinds of lasers. But in fact, it turns out they're not. And this is some numerical modeling of our own, which just showed how if you study such a laser in detail, you can certainly find regimes of stability, which are the green regimes, but you can also find more complex regimes of double pulse and triple pulse and chaos. And you can measure all sorts of, you can model all sorts of spectral and temporal instabilities inside such lasers. And what's nice is that you can actually see these in experiment using the dispersive Fourier transform. You can see remarkably rich and complex spectral dynamics, and through numerical autocorrelation, temporal dynamics inside such lasers. You can also answer fundamental questions of what happens when you turn on such a laser. When we turn a key, our laser becomes stable, but in fact, for about 100 milliseconds, there are all sorts of things going on in a passively mode-locked laser. And using these real-time techniques, it's now possible to measure these build-up dynamics. And the key point here, and what makes these experiments both interesting and difficult, is that we've combined the dispersive Fourier transform with the time lens in a synchronized way to look inside this point here, just at the transition point between instability and stability. And because you measure the time, because we have a time lens and a dispersive Fourier transform, so we get real-time measurements in time and frequency, we can use a Gershberg-Saxton deconvolution to reconstruct intensity and phase. And we can see breathing in the solitons just before instability and stability just after that transition to stability. So these are experimental measurements of the soliton buildup over 200 round trips in the laser. And you can also see much more complicated things if you look a bit earlier in time, before the stability onset. When you just want to look at these instabilities, you can see beautiful things like soliton collisions, both in frequency and in time, and it's just fantastic to be able to look into that. So the conclusions are that in terms of the initial idea of extreme events in rogue waves, the rogue waves in optics can emerge out of fiber nonlinear dynamics due to noise sensitivity of soliton propagation and modulation instability. However, in both optics and hydrodynamics, it turns out that you can also see statistical rogue wave events using linear superposition of if you have enough waves that combine together. So linear superposition and linear focusing can actually generate these extreme events as well. In any case, from a pure optical context, real-time measurements have really opened up new windows into studying instabilities in fiber and fiber lasers. And these real-time measurements are essentially becoming necessary in experiments. Machine learning is promising. It's a field which is also going through a lot of hype at the moment. Where it's going in ultrafast nonlinear optics is still an open question. We tried our best to review that in an article a few months ago. And I think that at least for a couple of years, it's going to give us some new numerical tools to analyze and to control our experiments. So I think there's a lot of work where we can use machine learning to improve what we do. And that's going to keep me busy, at least for the next few years. So thank you very much. I'm sorry if I've gone over time, but I'm happy to take as many questions as you may have for those who are still here.
John, thank you very much. I think this was the perfect first talk in our DLS series, taking us all the way from the history of nonlinear optics to the latest in soliton instability, touching upon the different fields where rare events occur, and also pointing out that the Russians probably have done it before you. There are a number of questions, so let's jump into that. Nicola.
Hi, John. Thanks a lot. That was very nice. I have a question when you discuss this machine learning in the first place, because when you explain at the beginning this rogue wave event, it's clear that this is a single event, and then basically it seems to come out of nowhere. But then when you do this machine learning, you seem to say that still there will be kind of an history that will build up this rogue wave, so to speak. Am I correct, or did I, or how is the
okay? So yes, you're correct, but that actually answers a question which I didn't have time to touch on. But let's just go quickly and ask and describe what we're doing here is essentially trying to do a pattern recognition application of machine learning, where we're looking at the complicated spectra from modulation and stability, which seem far too complex to be able to interpret to see if there's a rogue wave associated with one or the other of the spectra, okay? And we're showing that in actual fact, if you go sufficiently far into the wings, the information about these temporal peaks is contained in these wings. In a sense, it's not too surprising because the temporal peaks are the shortest events, and the shortest events will contribute somehow to the structure in these wings, okay? Now, if you want to talk about whether the other problem is, this is why I said at one point, is this prediction or is this correlation? Yes. So
sorry, if I may interrupt, just to go in the same direction, if you go back one slide, my issue with this would be that this rogue wave is a single event, but yes, here when you do your rotating mirror, you do a multi-shot acquisition.
No, it's single. The mirror rotates to put. Is it 100?
Okay, you rotate and you get the whole picture of the whole thing. Okay,
yep.
like a bit like a street camera.
It's like a street camera, except you're streaking in between shots, and okay, on different points. But in terms of the other question of whether or not machine learning can predict a memory, some other stuff we've done just recently is precisely that. So this paper, which just came out in Nature Machine Intelligence, aims to replace the nonlinear Schrodinger equation, integration through split-step methods, by training a neural network to learn the local recurrence over about 5 or 10 round trips, or sorry, 5 or 10 steps in an algorithm, to be able to predict, model, simulate, right, the supercontinuum. So these are some results where we trained you give a neural network 1,000 simulations over all sorts of different soliton numbers. You vary the power from 500 watts to 2 kilowatts. And then it generates lots of different supercontinua. It somehow, using a recurrent neural network, manages to construct some transfer function, and then it can reproduce for a new problem. It can reproduce the evolution. The difference is that it does it essentially instantaneously, whereas the simulation, of course, needs to integrate. How far we can push this, I have no idea. I still find this a little bit magical, how these things actually manage to work.
Okay, thanks.
Okay, Annie.
John, thank you very much for this fascinating talk. I really enjoyed this time lens concept. And I was wondering, I mean, you mentioned that you use 4-wave mixing to put this phase, this quadratic phase on the, pulse that you would like to detect. So one can also use, for example, some frequency generation or any other second order effect. So I was wondering if you are using this third order effect just because it's easier with the fiber, or you need really high phase shifts that moves you towards this third order effect. So is it possible to do such a thing exactly with the second order effect?
Well, the magnitude of the phase shift determines the magnification, right? Because it's the strength of the lens. So we at best we get a factor of 100 of magnification. Okay, so we get about a factor of 100 temporal magnification. So a picosecond becomes 100 picoseconds, and that's 100 picoseconds today is still something you can measure with a fast photodiode. So that's great, right? I haven't. Why we used this was because at the time we could buy it in a box. So they're not sold anymore. So it was sold by these silicon chips were fabricated by Mikael Lipson, who I understand will be speaking at the end of the sequence. So that's a nice frame. And at the time, Thor Labs put this into a box, and it all worked with a Menlo fiber laser that was pre-chirped to construct. It was all fiberized, so it was all plug and play, and it worked within the regimes that it worked. And we actually had to get some special synchronization electronics built by Menlo Systems so that it would work in the synchronized way.
So then in this system, you had 100 times magnification,
yes.
Right? Okay, perfect.
Yeah. You can go to about 150. The problem is that the more magnification you get, the lower this signal becomes on your stretched oscilloscope. So if you've, so then these 40, 50, 45 gigahertz scopes, their own dynamic range is maybe is not great, right? You might get 8 bits or so on, and so you can get digitization noise if the pulses spread out too much. So it's a compromise with the detection bandwidth you have and the dynamic range.
Oh, beautiful! Thank you very much.
We haven't tried second order effects.
Yeah, I think you get for sure less of the phase shift, but yeah. Thank you very much.
But you maybe get less phase shift, but you might get more signal. So
true. That's true, actually. Right. That's true. It's more efficient, right?
So yeah. We no matter what experiment we do, we never actually seem able to get everything we want. Right?
Yeah. So thank you very much.
Okay, that's right.
Okay, we have 2, 3, 4 more questions suddenly. Sven, are you still here? Do you want to unmute yourself and ask the question?
My question is, what role do sea quakes play regarding high sea waves in the parable between water waves and light waves regarding to the nonlinear Schrödinger equation? That's my question.
So that's interesting. So if you consider, well, the idea of an earthquake triggering a giant wave is something that happens, but it usually generates tsunamis, and tsunamis involve a very large displacement of a water volume, but the initial height of a tsunami is maybe only a few centimeters. But the velocity of a tsunami is very large. And so a tsunami then propagates over large distances. And as it approaches the shore, the fact that the ocean depth decreases compresses that volume of water that was displaced into a very large wave that then causes great destruction. Now, that kind of tsunami compression, that can be seen in optics, but it's not through the nonlinear Schrodinger equation. It's simply through linear pulse compression in something like a dispersion decreasing fiber. So if you were to just take a light pulse and propagate it linearly in a waveguide where the dispersion changed, then that would be analogous to the change in ocean depth with distance that would cause a tsunami to increase in amplitude. So that's the simplest explanation. Now, it may be that small underwater earthquakes generate noise conditions on the surface of the ocean that can generate this initial modulation that will grow through modulation instability as well. So I think there are two answers to the question. One is that in the case of the tsunami, probably the correct analogy with optics is through pulse compression in an environment where the dispersion is changing. Another possibility in the nonlinear case would be of changing the initial conditions to generate noise.
Yes, thank you very much indeed.
Okay, John, we have a number of more questions, but we're also rapidly running out of time. So I would suggest...
Well, I'm not running out of coffee, so that's fine.
That is good, but you also still have 2 hours to go, right, with other meetings. So I would suggest that for everyone who still has questions to either contact John directly or to wait until we can hopefully welcome you in person at the Institute, and then we can continue these discussions. So thank you very much again for a really fascinating, brilliant talk, Q&A. Thank you very much. Before I let everyone go, John, if you want to, you can switch to the other Zoom room already. But before I let everyone else go, I have something that you've seen already. So this is the series. I want to point out that we have the next DLS seminar already next week on Thursday at the usual time by Stefanie Wehner from Delft University. She will be talking about her view on an approach to building a quantum internet. With that, thank you everyone for joining, and I hope you have a nice afternoon, and I'll see you again next week. Bye.